Can anything be a spring?
Yes.
Yeah, that's a good answer, right? So anything can compress. So let's look at an example of what might be a spring, right? So we have an equivalent stiffness of a structural system. Right, and so let's take a rod with a uniform cross section. So let's give it a fixity and a length L. And let's say we have a displacement down as X, right? So I want to know what the stiffness of this mass vibrating is. So how would I start? What's my first step here? Free body, right? Free body diagrams solve all problems in life. When my friends have real problems, I tell them that, and they go, "What's a free body diagram?" And I say, I don't have a lot of friends. That's probably one of the reasons I make jokes like that. Okay, so, well, we can do a free body diagram. We'll get that. But right now, let's just kind of draw it as a spring, and then let's work through our mass, our variables for how we're going to get this, right? So we want a stiffness. Let's see how I do this. So we want a stiffness K, right, which can be defined as our force over our displacement, just kind of rearranging Hooke's law, right? So for the stiffness of the spring, to be more closely related to the materials of the property, so let's go. So this is Hooke's law. So for the, let's go for the rod, or nope, let's not say that. For the spring to be more related to material properties, we can express this as our stress in our material is equal to our Young's modulus times our strain. That makes sense? Right? So that's something from mechanics. We can expand this out, right? So what is stress? Yeah, perfect. That was Lawson. Okay. I'm getting, I don't know. We'll see how this goes. Force over area. And then the strain is our change in length over our initial length, right? And what have we defined in all of these systems for our change in length? What's the variable we're using? X, right? So we have our Young's modulus times our X over, and then if you scroll back up, our initial length, I called it capital L, but I'm going to call it lowercase l here. Did I call it capital L in the note? Nope, I just transcribed it wrong here. So let me fix that. There's a lowercase l. All right. X over L. So we can rearrange these terms because to get back into Hooke's law, right? So to get back into this, we can end up with K is equal to EA over L. Right? So this quickly becomes a stiffness that we can solve for our rod. Does that make sense? So E is our Young's modulus. Let's say it's aluminum, right? So aluminum's 69 gigapascals, I think, or 6.9. Area, length, those are things we can measure. Right? Pretty simple. So now we can get, we can convert a rod into a spring. That makes sense? Any quick questions on that? Pretty simple, easy squeezy. Okay, so let's go ahead then and look at a cantilever beam. So this one's a little bit more difficult. This laptop is getting hot. Let's try this. Okay. Trying to keep it from shutting down on me, which happened in the past. All right, so we have a cantilever beam, right? How do you draw this as a spring mass diagram? Avery? Is Avery here or online? Avery, are you online?
Yes.
Yeah. How do you draw this as a spring mass diagram, Avery? Oh, you can't really see what I'm pointing at. How do you draw this as a spring mass diagram? So in class, I do point at the board.
Yeah. I would turn the rod into a spring, and then
So maybe something. Would you do something like that?
Yeah.
Okay. So where are you going to put the mass then?
I would attach it to the end of the spring there, like it is on the left.
I mean, I like the thought process, but which way is the displacement moving?
The displacement's moving down. Would you have to turn it vertical?
Yeah. So maybe what if we put the spring up like that?
Yeah. Yeah. That looks
And then
better.
get rid of this other one?
Yeah. Make it easier to get the displacement.
Yeah. So, and we have to do that because we have 1 degree of freedom, right? And that has to be in the direction we're considering, right?
Right.
Perfect. You can't see. There's no points related to me putting an X by your name. I'm just trying to ask questions to everyone. Okay, yeah. Thanks, Avery. Perfect. Yeah, so we want to draw this out like this. And I hope that makes sense now as to why we want to do that, because we have 1 degree of freedom acting in the vertical direction, right? Yeah.
Why wouldn't that be an angular displacement?
Because what are we defining here?
So x is downwards, but if the mass was to go down, it would go down like.
But we can only define 1 variable. So on a 1 degree of freedom system, we have to make that definition. And we made that definition here. If we had, that's a good point though, like if we had made the definition of what's the angle of displacement, then you might have to solve for that. But the truth is, on an angle of displacement, you're always going to have kind of 0 angle here because it's a rigid body. A little harder. Yeah.
So awesome. Change like our coordinate system, instead of from the first situation where it's just the rod and x is pointing down, like if you rotate it to where we have it as the spring, doesn't that change how the spring / rod moves and reacts?
All right, so it's like a bunch of questions there. Think about our mass here. All we're concerned about is how that mass moves in a direction like that. Did that make sense? Because that's what we've defined our x as. So we're only concerned about the mass going up and down vertically, right? All models are perfect. All models are wrong. Some models are useful. This model is wrong, right? But useful, yes.
So we keep our x in the same direction because that's the one we defined, right?
Yes.
Okay.
Yeah, that's the choice we made. Life is full of choices. I don't know what choice I made today.
So is it just matters where the x is pointing, and you would position the spring to be in that same direction?
Yeah, so the spring only acts in 1 direction, right? A linear spring is only going to act in tension and compression. And then it matters because if this is your engineering system, this is the direction you want to know displacement in. You're the engineer. You chose the fact that you want to know the vertical displacement. If you wanted to know the horizontal displacement, then we have a different story. You chose that, right? Your boss said, figure this out, and you said, well, I really only care about my horizontal displacement. There was one other question. Go ahead.
So you have a horizontal system. This this case.
No, we don't. We have a vertical system.
Okay, so a vertical system, and yes, we're going to rotate it, but it should be fine because we can find the cross section A of the beams, right? And then we can divide that by length.
Yeah. So what we want to do here is get what we want to do. I mean, is get our K equivalent, right? What is the equivalent stiffness of this beam that gives us this spring? That makes sense? Okay. So we can do that. Anyone remember how to calculate the deflection of a tip of a cantilever? Don't worry, there's no way I would know either. What? So have you seen this? Sigma is equal to PL cubed over 3EI. That look familiar? Like, oh yeah, right? That's what I think too. So this is going to give us our deflection, right? This is how we typically write it. So, but we're really concerned about X here. I don't know why my X went away. And we're just going to call that sigma because that's, how we typically write it. So if we transform this into a system, we want to change out our P for F, our sigma for X, and thereafter the point load is replaced with an equivalent force F generated on the mass, right? So we're going to put an equivalent force F on the mass. So before, if we know the system, so the system can be expressed so our system is expressed as K is equal to 3EI over L cubed. Oh, sorry. That is Y. I don't think. Sorry. Our system is, come on. X is equal, sorry, K is equal to F over X. I have an error in my notes. Someone almost got extra credit. Maybe I get extra credit. All right, so we can show if we convert some of our terms, that K is 3EI over L cubed.